It's almost time, so I think we can begin the afternoon session. Let me introduce Professor Hyun Kim briefly. He received his PhD degree from KAIST Korea, and after that he joined Samsung Display Korea, and there he developed OLED display drivers. And then from 2015, he joined the Danguk University in Korea as an assistant professor. And then since 2019, he is with KAIST, School of Electrical Engineering. His research interests covers display drivers, power management, and the sensor readout circuits. Professor Kim is currently a TPC member of A-SSCC, and the TPC subcommittee chair for the CICC. And he is serving as the distinguished lecturer of the Solid State Circuits Society for the term from 2024 to 2026. Please welcome Professor Kim.
Thank you for a great introduction, Professor Liu. Hello, everyone. Good afternoon. I'm Hyun Kim from KAIST, Korea. And I'm very honored to be here to give my talk in the A-SSCC 2024, the Circuit Insight. So today, I would like to share with you about the accelerating response speed in analog circuit, the design techniques and insight. This is our line. And I'm going to talk about the basics of the speed of analog circuit. After that, we're going to briefly review the frequency response of buffer amplifier, and then the slew rate limitation. And finally, we're going to investigate the frequency response in the multi-stage amplifier design. Okay, let's get started. Okay, we all want the energy efficient and high-speed circuit because there are many various variety of the analog circuit building blocks, such as the buffer amplifier, driver, the switch capacitor amplifier, comparators, it's like that. And modern electronic system contains and composed of the key analog building blocks. The response speed of this analog circuit is dominantly determines the overall processing rate and throughput of the overall electronic system. Therefore, accelerating this response speed of analog circuit is very key in modern era. However, in most of the conventional analog circuit design, there is a clear trade-off between the power consumption and the speed. This is the example of the display driver circuit system. By utilizing the low frequency and low speed the driver circuit, we can save more the power consumption, so we can extend the power usage time. But due to the slow response circuit, the frame rate could be limited, and the user must experience uncomfortable the motion blur. On the other hand, with using very fast driver circuit, we can enhance the frame rate. Therefore, the user can experience more the smooth transition in the movie images. So, however, as I mentioned before, the high-speed circuit require the higher power consumption. So the power, the speed are a clear trade-off. So even there are very variety of analog circuit. So in this talk, we're going to explore the energy efficient and high-speed design strategy based on the buffer driver circuit. Okay, this is the buffer circuit configuration. So as you see, this buffer is widely used to drive the signal and stable voltage regulation. For here, input signal, this signal is delivered to the capacitive load by using this buffer amplifier. This is used in the display driver, as we discussed before, and the data converter, the input side, and the sensor interface. And with a fixed reference voltage, we can utilize this configuration using the voltage regulator. So then, even if the load current change, we hope to achieve very stable voltage at here. So that kind of the circuit configuration can be used in the LD regulator or the common voltage buffer. Right. Okay. Depending on the response speed of this amplifier, you can see the input signal delivered to the load with the high speed and low speed. Right. everyone wish to deliver the signal very fastly, but using the very slow amplifier, the settling time become longer, right? And in the perspective view from the voltage regulation, when the load current change, the output side of this amplifier must experience the voltage drop, but this response speed is very fast. The voltage drop can be minimized, but the amplifier is designed to be very slow. Then the output signal must be up the large voltage drop must appear at this the V out node, right? So conclusion is very clear. We need very fast response the amplifier design. Okay, so turn our attention to frequency response of the buffer amplifier. Okay, so this is basic structure of the amplifier design. This is the differential input pair, and the upper side is the current meter, right? Therefore, the differential input pair provide the transconductance, I mean the input voltage difference convert to the current, right? And that current sum together and convert to the single output, and then we can see the output resistance from the output side, which is the modeled in the RO in the small signal domain. So we can model the single stage amplifier as like this GM and RO, right? Okay, so open loop gain can be defined by GM times RO, right? However, if the output port is directly fed back into the input side, then we can make a unit gain buffer configuration. So here, this negative feedback work to minimize the error in the two voltage difference. Therefore, the V out will track to the V in, even they are physically connected, right? So this is called the buffer. The V out follow the V in. Okay, before this is the open loop configuration. Then in the frequency response, must has a pole frequency, which is formed by output resistance RO and output capacitor CL, and which can be located at a very low frequency because of very high capacitive load and high resistance of RO to boost the small signal gain. But in this unity gain buffer configuration, the closed loop frequency response transformed to as like this, right? And then, as you can see, this is the closed loop transfer function. So you can see this point, which is for the view from viewpoint of the open loop, this is the unity gain frequency, actually works as the 3 dB frequency in the closed loop configuration. And so this is the 3 dB frequency, therefore that actually works as the time constant for closed loop amplifier. So keep in mind 1 over omega t, which is omega t is the bandwidth. The 1 over bandwidth is actually works as the time constant of the closed loop amplifier. So omega t is larger, then time constant is shorter, then the more faster response. Okay, so as I mentioned before, this is the time constant and the time domain response, which can illustrate the relationship between the time domain, the response, and the bandwidth in the frequency domain. Okay, so from this waveform, we can conclude that maximizing this omega t, the bandwidth maximizing, is necessary, more shorter the settling time. Okay, but here, the bandwidth is determined by the transconductance and the output capacitor CL. However, the CL capacitance is the uncontrollable factor. Therefore, we need to maximize this transconductance more higher and higher, right? More faster the response of this speed. Okay, so so far we have seen why the bandwidth is determined by transconductance, but it's not intuitive. So this slide shows why the higher GM transconductance accelerated the response. Okay, in order to track the V out, actually, in order to change the V out, the charging or discharging current is necessary, pouring into the CL capacitor, right? And this output current comes from this transconductance cell, and then this out, therefore, can be modeled by output current, which is equal to the transconductance times V out minus V, right? And initially, the difference is very large. So if the GM designed to be very high, we can generate the initial very high current of output, right? So this is the two design with the small GM, and the other one is the higher GM case, right? So then with higher GM, the output current can be more maximized. Therefore, the larger current pouring into the output capacitor, so we can achieve more faster response of the output, right? So as you can see, we can understand without using any mathematics, we can understand that, oh, high GM, very good to accelerate the circuit response in the time domain, okay? Okay, so turn our attention to maximizing the transconductance. Actually, this transconductance is determined by the aspect ratio, size, and the bias current, okay? So as you see, in the CMOS, the transconductance implemented the design. The transconductance is proportional to the square root of the bias current. The bias current is here, IB. So the doubling IB to increase the transconductance will increase only GM by the 41%, right? So this is actually very inefficient way to increase the GM by just increasing the current. So we can conclude that increasing transconductance require the larger power consumption, right? Therefore, we can realize that, we can recognize that transient response is trade-off with the power consumption. Okay, so this slide shows another way to increase the effective transconductance by using non-symmetrical current meter. The current meter is good current amplifier, right? Therefore, if we're using the non-symmetrical current meter, I mean not one-to-one current meter, then we can use rather than we can use 1 to K ratioed current meter as like this. This is the transistor level implementation, and this is the abstracted figure. So as you see, the input pair generate the GM, but if we're using the 1 to K the current meter, we can boost the transconductance K times GM. This is very straightforward, right? However, this is very good way to increase the transconductance, but the static power consumption also increased by a factor of K, right? So total IDC, the static current consumption, also determined to the 1 plus K IB, right? Okay, so this is therefore GM can be boosted by 1 to K current meter, but the power consumption also increased by 1 plus K factor, right? So this is the clear trade-off, right? So the trade-off between the bandwidth and power can be evaluated by the figure of merit. So this is a figure of merit. This is the bandwidth over total current consumption. And bandwidth is determined by the transconductance over CL. Therefore, we can rewrite this, the FOM equation is to be K times GM over 1 plus KIB, right? So this is the clear trade-off, can be more explicitly that can be seen. So our fundamental question is how to improve this figure of merit. I mean, how can I increase the transconductance without increasing the power consumption, right? Okay, this is very simple method, the solution to break through this design trade-off. Compare with the conventional design, I just add a simple current source here. This is the breathing. I want to call this one the breathing current. This is IB over 2, right? Even though the attachment is this IB over 2, in the small signal domain, the operational behavior is the same with the conventional design, right? So then the small signal domain, the GM, will be boosted to the K times GM, right? Anything not changed. But in the current consumption, the only remaining of current will be copied to here with a factor of K. Therefore, we can reduce total the current consumption, right here. So in this design, the figure of merit can be slightly improved and better than conventional design of figure of merit, right? This is maybe approximately 2 times increased, right? Okay, so then we have a hint. So how to maximize this opportunity? That is kind of design is the nested current meter design. Okay, in this design, the 2 transconductance cell are used. One thing is the plus GM, the other one is minus GM. So you can see in the small signal domain, the minus GM current is copied but opposite direction with a factor of K. And then the plus GM and here K boosted GM summed together and copied to final output. So the effective total transconductance can be expressed by 1 plus K times GM, right? On the other hand, the large signal domain is different. So the IB current consumed, and this is copied to here, but then only remaining current will flow through here, so the copied to only remaining current, right? We can observe that here, that is the plus K, here, but it's the minus K, right? This is the opposite work, right, for the K factor, right? So then we can see a good opportunity and on potential to increase the GM without increasing the power consumption by using this kind of design, right? So how this key idea is derived? One of the limitation of the conventional current emitter actually is the current emitter, the working behavior is the same in the small signal domain as well as the large signal domain. By approaching this, we can separating the behavior of the current emitter. So the key idea is the current emitter behaves differently in large signal domain and small signal domain, right? So we can break through the limitation of the current emitter. So let us compare the figure of merit, right? So here, this is the conventional design, and here is nested current emitter design. Okay, then if we select the K is close to unity value, then the current flows through here become very, very minimized, right? And analytically and numerically, the FOM, if the K is selected very close to unity, two design consume the same power, but the transconductance will be boosted by 2 times. For the same power consumption, the transconductance can be boosted by 2 times, right? So that is very good approach, right? Okay, so this principle is not difficult and is very easy to apply in our circuit. So from now on, we're going to do practice using this nested current emitter design. Okay, so let us start the very conventional NMOS differential pair operational transconductance amplifier. Okay, in order to accommodate the upper range of the input common mode range, so then we can use the NMOS pair, and this is the NMOS input pair design OTA. And in order to accommodate the lower range, the common mode voltage, we can add the PMOS input pair OTA, right? And then these two design sum together, and then we can accommodate the rail-to-rail input range. This is the conventional rail-to-rail OTA amplifier, right? Okay, then in this design, this is very conventional design. So then effective transconductance is the sum of the K times GMN plus GMP. Each respectively comes from the input NMOS input pair and PMOS input pair. And total, the static current consumption will be defined to be as like this, 3 plus K, right? As you see, the clear trade-off can be observed. Here, the proportional to K, here also proportional K, right? How to achieve the nested current emitter design? Very simple. Just insert the 2 transistors in the conventional design. So just inserting the blue transistor here and here, we can realize and implement the nested emitter, the rail-to-rail operational transconductance amplifier. The merit is obvious. So as you can see, the Ka, actually this is the meter ratio. GM can be increased by the Ka, but the total DC current will be reduced by the Ka. You can see this is minus Ka, right? So for the same value of the Ka, Kb equal unity, then just inserting Mn, Mp, the 2 transistor, we can improve the figure of merit, the 50% increased, right? So very simple approach, but the result is amazing, right? Okay, let's turn our attention to the slew rate limitation, right? In the small signal analysis, we can hard to see the slew rate limitation, but in the perspective view from the practical, the transistor level implementation, the maximum drivable output current is highly limited. So this is the transistor level circuit implementation. And when very high difference voltage is applied into the differential pair, then one thing is turned off and the other one is fully turned on. Therefore, the fixed tail current is directly copied to the output stage to charge the output capacitor, right? And therefore, even if a very large input difference is applied, the maximum drivable, maximum available output current will be limited by the tail current bias IB, right? So then we can define this limitation by using the slew rate. The slew rate is the maximum voltage changing rate for the time, right? And the voltage change at the Vout is determined by the current, charging current, and the capacitor. Therefore, slew rate is can be expressed by IB over CL, right? So this figure shows the two design. One thing is that these two waveforms are simulated under the same transconductance, but the other one is without the slew rate limitation. The other one is with the slew rate limitation. And their response speed clearly different. Okay, so what is the contribution? Which one is more dominant between the slew rate and the bandwidth? Which one is more dominant? So this is the initial voltage, and this is our target voltage to be arrived at the output. And depending on the settling accuracy, the settling accuracy is aimed at just 10% of error, then most of the response time is contributed by the slew rate, right? This is over the 90%. And if you aimed at the 1% accuracy error, the slew rate and bandwidth contribution is half and half. And if you want to achieve very accurate settling accuracy, then the bandwidth is more important, right? So as you can see, the slew rate also not negligible contribution in the transient response. So maximizing slew rate is very important. Okay, so how to maximize the figure? How to maximize the slew rate? So okay, we can also in this time we can reuse the current meter design, right? So in this design here, the maximum drivable output current is limited by IB, and here total static current consumption is 2IB. Therefore, on the other hand, the other one is using 1-2K current meter, right? So due to the current amplifier by a 1-2K current meter, therefore we can more maximize the output current that is boosted by K times IB, right? But as I mentioned before, current meter behavior same me working in the large signal domain and the small signal domain, right? So therefore, the static power consumption also increased by a factor of K, right? Okay, so the maximum slew rate and static current consumption, they are highly closely correlated. Therefore, we can evaluate their relationship. So this is the slew rate perspective figure of merit. This is equal to slew rate times CL over IDC, and that can be rewrite by canceling the CL. That is determined by maximum drivable output current over static current consumption, right? Okay, so our mission also clear at this time, how to maximize the maximum drivable output current without increasing the static current consumption, right? From now on, we're going to explore some design examples. Okay, we can, here, this is the conventional design, and then we can boost tail current only for the initial response time, only for during the slewing period, right? Okay, so the black line is without the tail current boosting, but the blue line response is with the tail current boosting technique. So only the initial driving period can be detected by this comparator, and then comparator detect the initial response, then closing the switch here, then initial response duration, the IB plus the boosted current can be added to the total tail current, so we can maximize more current. But in the steady state, then the input voltage difference is very small, then the switch is turned off, so only IB current consumed, right? So then, therefore, IB plus the boosted current is only activated during the slowing period, so we can achieve low static power consumption and the high slew rate, right, simultaneously, right? However, in this kind of approach, the comparator performance is very important. So there are many the non-idealities in designing the comparator. So offset voltage and limited sensitivity and propagation delay in the comparator design, right? So this non-ideality can be referred into the input side. This is the modeled as the VOS. And if VOS is the positive, then we have to, this slew enhancement is early decay, right? Or the offset VOS voltage is lower than 0, then unwanted, undesirable overshoot must be appeared at the output, right? Therefore, designing this, the comparator ideally is very critical. So, how to generate the high-speed reaction the comparator? The comparator also need the high speed, and high-speed comparator necessitate high current consumption, right? This is the sound like the contradict, right? Okay, and in this design, the fixed boosted current is used, but we can adaptively boost more further the current by using another type of the circuit. Okay, so the tail current is generated from this circuit here, and there's the input is also input to here, and this is the source-coupled transistor design. This is NMOS and this is a PMOS, and they are PMOS, NMOS as coupled in the source-coupled, right? Okay, so if the V in, V out, their difference become larger and larger, then their voltage difference, delta V, is this is proportional to the square of the voltage difference. The current will be generated from the left side circuit, right? So the boosted current is the proportional to square of the voltage difference by using large signal V to I conversion behavior of the MOSFET, right? You know, the current of the MOSFET is proportional to square of the voltage squared, right? So then we can more maximize the boosting current. This is the proportional to delta V voltage square, right? So then for very high voltage difference is applied, then very boosted current will be generated, and that will be helpful to accelerate the slew rate response, right? And also, this left side circuit must be turned off during the steady state. So then the NMOS, PMOS threshold generate a certain dead zone. So in this dead zone, the left sides of the boost enhancement circuit are automatically turned off, right? So then only static power consumption, therefore only IB, right? But the boosting current is very highly increased by the proportion to delta V square. Okay, so this is another design for slew enhancement, right? So left side is the conventional, the operational transconductance amplifier. The right side is superclass AB OTA, right? This design looks very weird and not conventional, but small signal domain behavior is very similar to the conventional OTA design. So in this design, the differential pair is biased with the fixed tail current. But here, instead of using the fixed tail current, the two source coupled, the two source follower, the voltage split source follower is used in the tail side. So biasing is very simple. If this transistor and this transistor, the two transistors are identically designed, so this transistor and this transistor, all the transistors are biased with the IB, and here the most bottom side transistor work with the 2IB. So and this is consume more higher power, but the small signal behavior is very similar to conventional design. On the other hand, in the slewing behavior, it's very totally different. As we discussed before, IB current fully turned due to this fixed IB current fully charge or discharge the output capacitor directly. So our maximum drivable current is limited by this fixed tail current. But in here, these two transistors simultaneously turn off, differential pair and the source follower. So these transistors turn off, then this fixed bias current of IB directly pull up the gate of this transistor. So the most bottom side of this transistor can be fully turned on without any limitation, right? So then this differential pair side source voltage can directly tied to ground, so then we can maximize current more higher further without the limitation of IB, right? So then maximum drivable output current is proportional to delta V square rather than fixed the tail current IB, right? So then in this case also we can maximize the slew rate figure of merit without the constraint of the IB current. Okay, this is a simulated result, right? So in the steady state, the power consumption, in the static power consumption, only the 50 nanoamps. But for very large input is applied, approximately over the 3 volt, the voltage change is applied, then the maximum drivable current is boosted to 154 microamps. This boosting factor is over 3,000 times higher, right? So the figure of merit is actually defined by maximum drivable current of over the IB current. The conventional design is very close to FOM, close to unity, but this design can achieve SR. Figure of merit is close to 3,000, right? This is the big change. Okay, so we can also modify, we are able to modify the current meter. Okay, so compare with the conventional design, we can add the cascode, but this cascode stage is the cross-coupled, right? And very small change in the small signal domain operation, the two transistors work very similar because this cross-coupled transistor just works as the cascode stage. There is no big contribution to small signal behavior, right? But when large signal voltage is applied, so here, then this side, left side differential pair is the turn off. So then there is no current. Therefore, the gate voltage is the pull up to the VDD. Therefore, then the PMOS cascode actually cross-coupled transistor will be fully turned off, right? So this path is the closed. This path is open. Therefore, this loop cannot work as the diode connection, right? Due to this path is open, right? Therefore, this IB current directly pull down the gate of this node, therefore up to the close to 0 volt. Therefore, very maximized current, which is proportional to delta V square. This is the intrinsically generated by the MOSFET V to I conversion, that the high boosted current will be supplied to the output, right? Okay. So far, we have discussed the design with the pure capacitive load. How about the buffer drive with R plus C load? RC load, the pure capacitive load, is the real response is totally different. Okay, so how about this? This is the transmission line, the parasitic resistance and parasitic capacitance, right? This is our real target signal to be delivered, but this is the buffer output, right? How about the difference? So this node voltage more rapidly responds compared with the pure capacitive load, because when in order to change the V out, the current is applied, and the supplying current generate a direct voltage appeared across this the resistor RL. Therefore, large voltage IR drop appear across here. Therefore, this direct voltage appeared across the resistor aids in the rapid reaction of the buffer, the feedback loop. So as you see, the red line is the buffer direct buffer output, more fast response compared with the pure capacitive, the load buffer amplifier. However, in this RC load system, our actual interest is here. This is target node voltage, right? Even if very fast response can be achieved at here, this signal must experience the load time constant to deliver to here, right? So this is the time constant is the physically constraint and we cannot overcome, right? Therefore, this is the blue line is the response of this node. Therefore, this response is very response with the tendency of the load time constant RL and CL, right? So there is any way to overcome the physical limitation of RC time constant? This RC time constant is the given for the system or environment, right? Okay, so in order to overcome this physical RC time constant, we can use the pre-emphasis technique. The pre-emphasis technique is very well known in the buffer design as well as the signal drive or the signal interface circuit. Key idea is very basic, right? So actually, we want to change the voltage of delta V at here, but more overly sized amplitude of signal is applied to initial duration with a factor of K, right? In here, the K is pre-emphasis ratio. So this is the original signal drive, but the pre-emphasis signal is applied at the initial response the duration, right? Okay, so this is the without any pre-emphasis driving, so the response is must follow the time constant limitation, right, of the RC, right? And with the pre-emphasis technique, more sharpened and very fastly respond, the output can be achieved by using the pre-emphasis technique. But the K factor is very critical. With using the optimum K, then we can achieve very ideal response, which is overcome the load time constant, but the K factor is too strong, then we have to measure, we have to observe unwanted overshoot out here, right? Or the K factor is very low, the pre-emphasis ratio is low, then the signal response speed is not sufficient, right? So that is in this kind of the optimal, the pre-emphasis driving, the optimum, finding optimum K ratio is very critical. Okay, this is the rest part of my talk. Turn our attention to the frequency response in the multi-stage amplifier design. Okay, so far we have explored the single-stage design, but very, very frequently the multi-stage design is used. The reason why is using the two-stage design, the loop gain of the feedback loop, the loop gain become more higher, right? In the DC domain, the higher loop gain provide more accurate the response, right? So this is why I believe this is very well known. The DC state, the accuracy is proportional to 1 over T, right? Therefore, if we increasing the loop gain T more higher T enables more accurate the voltage deliver, right? And also one more additional the merit in the multi-stage design, right? So we can frequently use the second stage with push-pull output stage, right? Therefore, the push-pull stage has a more strong the drivability. So then we can achieve more higher the maximum the drivable output current by using this design. And also the VO1, this node voltage swing amplitude can be minimized as a factor of the second stage gain, GM2RO2. Therefore, we can minimize the voltage swing at the first stage. And due to using this the push-pull amplifier, we can achieve the rail-to-rail the output at the Vout, right? Therefore, the multi-stage design frequently used. However, when you're utilizing this kind of multi-stage amplifier, the stability must be carefully considered, right? We can observe the two significant pores, right? The one thing is formed at the output, which is formed by the RO2 and the CL, the load capacitor. And the other one is formed at the gate of the second stage. this the omega PG. This is formed by RO1 and CG, right? And mostly the GM2 designed to be tended to be designed to be very high size because to achieve high drivability. So input capacitance is not negligible. Conventionally, the input capacitance is very high. So therefore, these two pores is very likely to be very closely spaced, right? In this two pore closely spaced case, then the stability is become lower. I mean, it is very hard to achieve the sufficient phase margin, right? For better the stability or higher the phase margin, the recommended design is the output pore is located at very lower than the unit gain frequency, and the second pore, the non-dominant pore, must be higher than the unit gain bandwidth, right? This is the recommended sequence of the pores and unit gain bandwidth, right? This is dominant pore. After that, unit gain bandwidth, point, and then the second pore, right? So in order to achieve this kind of design, we have frequently used the Miller compensation technique, right? I believe all of you guys are very familiar with this Miller compensation technique. Okay, so the Miller compensation, just inserting the CM capacitor between the input and output of the second stage, then is from perspective view from the output of the first stage, the CM can be boosted by the second stage gain, right? Therefore, this node, the effective capacitance is highly boosted. So as a result, this pole formed at the gate can be moved to a low frequency, right? Okay, so by sacrificing the pole moving to a low frequency, then we can, this is very helpful to ensure higher stability, right? So as you can see, the pole is moved to a more low frequency, and then the bandwidth of this amplifier can be defined by GM1 and CM, right? Because the GM directly supply CM, then reach to the output, right? Okay, this is very understandable, and Miller compensation is we have studied several times in the textbook level. And one more, the output pole can move to a more higher frequency point, right? And why? The pole formed at the output is moved to a higher frequency. That analysis is actually handled by mathematical procedure in many textbooks, right? But it is not intuitive, right? So on here, we're going to understand why the second pole moved to a more higher frequency point, right? That is, okay, so the Vout change is fed back into the input side, right? So for the reaction of the Vout actually performed by second stage and first stage and the second stage, right? This is the original feedback path, right? But the CM provide a shortcut to react the change of the Vout directly at the second stage, right? This is more short path, right? So we can intuitively understand, oh, this is more rapid and very immediate response can be possible by signaling into the here rather than the original signal path, right? This is why the second pole is moved to a more high frequency. Okay, so CM, the Miller capacitor can generate the boosting the capacitance from the input side, but the CM provide a bypassing path, the shortcut path for rapid reaction to Vout change, right? So you can see one more local feedback loop is formed for benefit rapid change of the Vout, right? So the second pole is then totally changed to GM2 over CL, right? This is the big difference. This is big change, right? So by using the Miller compensation, we can split two poles, right? And then, okay. And however, the bandwidth must be lower than the second pole, right? So still, the limitation is alive, right? So how to maximize the bandwidth without a limitation of the second pole? That is, one way is we have to move the second pole more higher frequency to maximize the bandwidth, right? In this two-stage design, the maximum bandwidth is limited by second pole, right? Okay, by understanding, we can maximize the shortcut path. That is, if we can increase the gain in this local loop path, then we can move to second pole more higher frequency, right? So in order to enhance this shortcut path, we can insert the current buffer. If you insert this current buffer, then the loop gain is enhanced by Cm over Cg, right? The Cm over Cg, the factor is boosted. Therefore, the second pole moved to a more higher frequency. So the second pole limitation is more relaxed, so we can change and set to the bandwidth more higher frequency, right? The resulting the faster response, right? Okay, without using the Miller compensation capacitor, we can imagine more innovative circuit, right? So here, one example, hybridization of high gain and low gain amplifier. Okay, we return to the basic, why we have tried to use the multi-stage design. That is to promote more higher accurate DC level, the error for the DC steady state, right? So for low frequency range, most of the dominant response is handled by the two-stage design. And at the high frequency domain, in the high frequency domain, the bandwidth and the phase margin is highly limited by the two stages, but we can add one more pass. This is a single stage pass, and then we can signal transfer hand over to the single stage design. This is hybridization. Okay, so as you see, the final output is formed by the GM3 current and GM2 current. Therefore, the parallelizing these two amplifier is no problem. So before, at this point, the two-stage amplifier dominates the response. So we can achieve still very high gain. But at the very high frequency range, the overall feedback loop is dominated by the single-stage pass. So we can achieve the bandwidth GM3 over CL without any second pole limitation, right? So we can set the bandwidth to very high frequency point without the constraint of the second pole. Okay, and we can insert the buffer, right? So the gate pole can split into the two parts and move to a very high frequency. This is the original gate pole, but by insertion of this kind of the voltage follower, we can generating the two high frequency pole by utilizing the small capacitance of input of the voltage buffer and small up resistance of this voltage buffer, right? So then the high frequency two poles can be generated, right? So we can be free from the constraint of the second pole because these two poles are maybe located at very high frequencies, right? Then what is the equivalent the bandwidth? That is GM2 times the GM1 times R1, right? So actually, the first stage, GM1, R1, work as the boosting factor of the total transconductance, right? So this is the significant improvement. So how to design the voltage buffer, right? This is very hard because the equivalent second pole the two poles can be modeled to one equivalent second pole. But that is equal to reciprocal of 1 over omega, the buffer input pole and the gate pole, right? So even if we fixing the bias current IB, because the increasing IB is not ideal, so with the fixed IB, which one is the better design? The larger MB design is better, or smaller MB design is better, right? For the weak design, that I mean the very small design of MB, that is more favorable to reduce the input capacitance, but RB is somewhat larger. However, if the wide width of the MB design, then the RB can be significantly reduced, more strong the drivability, but due to increase the size, the CB is likely to be very large, right? So this is the trade-off. Therefore, optimum point is clear, obviously exists, and that point is determined by here. So still you can see that the second pole is a cube square of the IB. So this is highly power energy inefficient way, right? Okay, so this is another design to break through this limitation. This is the domino buffered design, right? So second stage design is split by n stage, right? So then the gate capacitance is split by n. This is the factor of n reduced by the split design. And the buffer also can have a reduced burden to drive, right? And this is the stage is cascaded as like this. This is also called as like a progressive drive, right? So the buffer pore formed at here is very small because the small design and weakly designed buffer, because this one buffer drive very segmented small, the second stage. And so the gate pore formed at here that is also reduced due to the split stage. The important thing is multiple gate pore formed. However, multiple zero intrinsically formed because the feed-forward path is formed. Therefore, this kind of n-stage domino buffer design, then the n pores is formed. They are located at very high frequency, but n-1 zero intrinsically generated. Therefore, effectively, equivalently, just one high frequency gate pore is remained, right? So this can be compared with the parallelized design, parallel buffered and domino buffered, right? For the same power consumption, the domino buffered design can achieve more the 70% higher the bandwidth, and 16 degree the higher phase margin can be achieved under the same power consumption. Okay, this is conclude my talk. We have discussed the basics of the speed of the analog circuit, and we also investigate the trade-off between the power and the speed, the bandwidth and the through rate, that they are highly constrained by power consumption. And also we have discussed about the high-speed design in the multi-stage amplifier design. Thank you for attention.